All right, welcome back. It's been a couple weeks since I had travel last week. Thanks for your patience with me. Just a couple announcements before we get started. First, we're going to start today with the homework discussion. I've had a few questions this week about homework. It's due Friday. I'd like to get your questions and try to provide answers for you as best I can to how to build the homework assignment as best you want. And then second, lecture today is how to do missing data with maximum likelihood estimators. I put it in the form of a handout. So it's not slides, it's a bunch of analyses. And we're going to talk a lot about them. I felt like at the end of chapter 3, I think I mentioned this a few times, there's a lot of things being thrown at you. Missing data with maximum likelihood, just another variable, yada, 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 right? I'm trying to sort through that a little bit and give you some better guidance. And at the end of this, we'll have like a little bit of a flow chart as to how to proceed as we go forward. Um, I will say that depending on how long homework and this discussion takes, this is quite a bit of information. So we may end up having this spill into next week. So that's the plan for the day's lecture. Upcoming next week, I will have a homework 3 out, but it'll be due after spring break. That'll be a homework on this topic that we're talking about today. So then I asked you to read chapter 4 between now and next week, and I'll have a reading assessment that I'll assign later today for you to do by next Tuesday. And then again, next week, we'll have whatever is left from today, and then an introduction to Bayesian with JAGs. Chapter 4 is an intro to Bayesian overall, or Markov chain Monte Carlo. And so that's where we're going to start. And then I'll teach you a little bit about how to use JAGs. And then we'll basically, after that, after we get back from spring break, we'll talk about how to proceed with analyses in Bayesian in JAGs. Although there are a few catches to what happens in the way things are described. So, does anybody have any questions for me before we begin fully? I don't think so. So then shall we continue? Let's go. Start off here. Let's start with the homework. So the goal for my homework assignment was to not just have you think about a maximum likelihood from a perspective of I'm using maximum likelihood, but really to think about how you're building the bits and pieces of it. The motivation for me for this, as you're going to see today, is that you can use, and pretty much everything in the world runs off of maximum likelihood. Pretty much every model you're going to want to do, with the exception of some real fringe ones, uses maximum likelihood, but not every version of maximum likelihood will give you missing data protection with the missing at random assumption. And so why I'm building this homework is to give you a sense of what maximum likelihood's actually doing, what a likelihood function does, and how we use it to go and find parameter estimates. Because that sense will help you in trying to decide when you build a model if you're using maximum likelihood the way you should in terms of the likelihood function itself. These are things that you don't often talk about. Like if you output a model, do you ever look at the log likelihood? You ever go there first? Anybody? I don't. For those of you listening to my voice on YouTube, I don't see any hands. I don't, but we're going to today because we're going to tie it all together, and that's somewhat important because, well, overall, this knowledge will not hurt you. In fact, it'll actually help you in trying to do estimation. So, what I had asked you to do, I'm just going to go through the homework, and as I go through it, if you'd like to stop me for questions, please do. Okay, I'll pause at every point to see if you have questions. Um, so the first thing to do is to simulate data, right? And simulating data, by the way, each of these steps in this example here are in my R file from we talked about. One of the R files either was maximum likelihood or one of the 2 weeks we did maximum likelihood actually when it came to building this. The functions for generating data, a normal variable, that's R norm, and a binary variable, that's R binom. Those will simulate random variables, simulate data. So that gives you a data set to work with. You know what the true value of the mean and variance happens to be in the normal distribution, and you know what the true value of the proportion for the binary variable happens to be. And so the trick in building your own estimation system is, if you know this, right, can you get close to these true values with your estimation system? So that's the first step in going forward. So we use simulated data to sort of test our approach, how we build it. Now, deriving the likelihood functions. This is the step I went through. Actually, let me back up here. Any questions about part one, simulating data? No questions too small, no questions too big. Okay. So again, our binom is the function here. And, sorry, our binom is for Bernoulli, and our norm is for normal. Okay. Moving on to part two. I asked you to derive the log likelihood functions. Now, I did this in class, particularly with the univariate normal distribution. So my slides actually have the derivation there. And I want you to go back and look at that derivation and try it to build it. Okay? This is where we use notation. If you're not familiar with how to use notation in a Word document or a Markdown file, I'm okay even if you handwrite it and take a picture of it and stick that picture in your response. That's fine with me. Doesn't bother me a bit. Okay? Now, so this is pretty basic in terms of I'm asking you to go back to my slides and repeat what I did. That's not a high level of understanding. So then the next step is a bit more challenging. Take the Bernoulli distribution and do the same thing. Right? That is taking the training wheels off to try to get you to do that as well. So you write out the likelihood function and then the log likelihood function for both. Now remember, in the process of writing a likelihood function, you start with the PDF. That's one observation's likelihood, right? And then the product of PDFs is the sample likelihood. And I remember saying likelihood, not log. But once you take the log of a product, it becomes the sum of the log of those PDFs. And that's what I'm looking for, the log likelihood function at the end. So those steps will still be the same. And then you can write an R function in R, or you don't necessarily, well, actually, you will need an R function to use on Optum. So embed those steps in R, basically sum the distribution for each person. Now, this last part, if you looked at my R example, you'll note that the normal distribution, you can get the PDF from it using a function in R called dnorm. And dnorm has an option that says log. Does the result come back as a log? And the answer is yes. True, you want that. So what these functions are really going to contain is a sum of the dnorm function with log equals true for each person in your sample if you give it a mean and a standard deviation, because dnorm needs a mean and a standard deviation. Similarly, in the Bernoulli distribution, I mentioned our binom generates a Bernoulli variable. Well, d binom gives you the likelihood function for it and the log for it. It works similarly. So you can again give it a probability parameter and then have it sum the basically the d binom for that probability parameter with log equals true across all the observations. So what this R function will do is take as input the parameters that you don't know. So for normal, that would be the mean and the variance. And as output, it will give you the log likelihood, just one number. That's what should happen. Right? So input again for normal, mean and variance, right? You tell it a mean and variance. It also needs your data, right? So your vector of data. So mean variance data go in, out comes likelihood or log likelihood. For Bernoulli, a little bit simpler, just the parameter pi goes in, the probability, it's its mean, and then out and data. So mean and data go in, and out comes the log likelihood. That's what I'm envisioning here. I have some syntax that does this for the normal distribution in previous classes. You should be able to see that either in slides or in the R file that goes as well too. I don't have the R binom. I don't believe I have the R binom in that function, but it should be a fairly straightforward switch. Does anybody have any questions on part two? And again, no questions too small, no questions too big. I respect all of your questions. I'm here to help. I believe in the value of this exercise, and I want you to help. I want to help get you to see the value of it, even if you don't believe it's valuable. Put that last part in. I mean, come on, doesn't everybody love deriving maximal likelihood? Yes, Kendra, you have a question. Okay, let me give you an example. How's that sound? All right. So first, I'm gonna generate data. We'll call it x equals our binom. Let's say 100 people. Size is always one for binomial. That's the number. So binomial is number of successes out of trials. Size is the number of trials, and a one trial binomial is a Bernoulli distribution. I'll use the probability of zero point 0.5. This is our data right here. Okay. So now, Kendra, were you asking how to write this in R? Is that right, or just in general? Okay, let's start there. Uh, Sorry, I went straight to code because I have R up and I'm primed to think code. But let's start with a Markdown document real quick and build this out. So first step is, can you, first of all, can you see, is my screen large enough for visual, for font and everything? Excellent. Okay. Step one is write PDF or PMF of Bernoulli distribution. So this is where you have to go and figure out the Bernoulli PDF. If you look online, you can see this. I can put this in text here. This is the PMF probability mass function is what it's called. But let me just type this here left. So this is the probability that x, a random x takes some value, little x. That value can either be a 0 or 1. And then for if you find it online, what you'll see is this is equal to the probability of a success, that pi parameter, the thing you're trying to optimize, raised to x itself. And I, of course, screwed that up right there. Uh, I don't need parentheses there. And then this is multiplying 1 minus that probability, 1 minus pi, raised to the 1 minus x here. So if you think about what this PDF is doing, pi to the x, when x is 1, pi is the probability of a 1. So when x is 1, you only get the probability back. But when x is 0, you get 1 minus its probability back. This part shuts off. Does that make sense so far? Great. Step 2 is write sample likelihood function. So really what we're talking about here is this is really for one observation I, x sub I. So if I put subscripts on all of these, you will see my x sub I. And next, by the sample likelihood function is now, remember, it's not a log likelihood, it's a sample likelihood. So really this turns out to be, let's see if GitHub Copilot suggests it correctly. How shall we? Huh? Uh, Let me save this. Yeah, let's save it right there. So turns out, yes, it did. What do you know? So the sample likelihood function, right? If you give it pi, it takes the product over all people, and it's the product of the PDF against all people. Is that making sense so far? Cool. Finally, convert the sample likelihood function to a log likelihood function. So now let's see what the GitHub Copilot works. Let's find out. All right. So basically, what you do here is you take the log of this term on the right-hand side. And what that ends up being, if I do that, I'll give you the steps in between. If you're like me, when I was doing this in class in school, my math was a little hazy, but how about I just do this? This is going to be the log of this product, right? The log of that product, we can re-express slightly differently. And, oops, there's the log of that. That term then becomes, if I take this part right here, uh, that thing will become the sum from I equals 1 to n, which is all of our observations, of the log of what's in the product. So this will be log right here, and that's this term right there. Oops, it needs in there. So far, so good? How are we doing? Okay, excellent. So if I'm going to keep continuing, I'm just going to simplify this a little bit more. Now, technically speaking, I didn't say how much depth to give, but I probably would give you full credit if you just kind of came up with this step 3 right here. And of course, I'm giving it to you, so be it. Hopefully, it gives us a chance to discuss this in class a little bit more. Um, but what you will see is the result that you see on this right hand side. If you do the algebra for this here, it's the log of a product. Basically, the exponents multiply the log of what that product is. So x times pi, that shows up from the first part, and then 1 minus xi times log 1 minus pi is the last part. You can simplify it all you'd like, but that's how to build it. Does that help answer your question? Excellent. Anybody else on this? Questions on this? Okay, let me ask a question to you then. I gave you normal in class. This was your challenge exercise. If I turn to you and say, I need a likelihood function for a Cauchy distribution, and you've never heard of Cauchy before, what would you do? What steps would you take? Thoughts? Ahmed, good job. Answer from the chat. Search for the PDF of the distribution. Same process. Number one, write the PDF down. So, where would you find Cauchy? Well, Cauchy's a fairly Cauchy distribution. The distribution function is the PDF is right here. Oh my goodness, that's ugly. Yes, it is. But the bigger picture is this process of building a maximum likelihood estimation program works the same. It's just you plug in a different PDF when you need it to be a Cauchy instead of a normal, right? Why this is important, in particular for today, is we're going to come to a situation where Lavon will not give us full maximum likelihood if we have a binary variable included. So in that case, Craig Enders suggests, or the book sort of suggests, using factored regression potentially. Factored regression, in the way that it's presented in the book, is he talks about an EM algorithm, and that EM algorithm turns out you can use an MLE, this maximum likelihood process. So I built an EM algorithm to show you this. Bottom line is I don't expect you to do that, but the point of the matter is this is the power that you have if you understand how to do this, is that no longer do you have to shove your data into a package and say, yeah, this one doesn't work with binary data, or this one doesn't work with continuous data, or whatever else. You can actually build your own stuff to do this. Okay? Let me tell you from my own experience, that's very, very helpful, particularly in getting people to pay you for consulting or otherwise. Pro tip. So, would anybody? So, how is that? That's how to find the likelihood function. The next part of the homework was right over here. Um, Writing R functions. Mentioned that before. Any questions on R functions? Kendra? Absolutely. A quick primer on R functions. I'll go back here real quick. So, a function in R is kind of like a macro in other programs. So, Lisa loves SAS, or I don't know if she loves SAS, but she's a SAS expert. I used to do a lot of SAS and then I quit. But like the SAS macro language, this is sort of what it does. It basically does the same set of code over and over again. But if I were to build a likelihood function, it'd look something like this. I'm going to start with R norm though, because I already gave you that before. The likelihood function would basically be, I'd call this normal log likelihood. So first you start with a name. and you set it equal to this word function. So when you do that, normal log likelihood running this, if you look at your R environment, it's a function. Just like our binom is a function, normal log likelihood is now a function, but one that you've defined. And I told you before we need to, oh, yes, I'll increase the font. Is that better? Can you see it better that way? Okay, great. Thank you. Here I need to give it the mean and the standard deviation and our data. Right? So far, so good? Oh boy. GitHub Copilot again did it for me. But remember what I mentioned. Dnorm is your function. Here, I'm going to take this apart real quick. Dnorm is, this will be the log, individual log likelihood right here. And then we can call sample log likelihood is the sum of individual. And then we're going to return the sample. So what happens in a function is it looks like R code, like you'd normally have it. The arguments of the function are the data you provide it, so that the mean, the standard deviation, and x. And then it functions as if its environment in R is devoid of any other data, right? So what you see down here, I have an x, but once I get into the function, that's like gone. I'll show that in just a moment here. And here, so if I change x to be our norm, n equals 100, mean equals, let's say, 10, and SD equals 1, and then I have my normal log likelihood down here. What I can do is I can go and call the function as I normally would. So normal log likelihood, I give it a mean, I give it the standard deviation, and I give it my values of x. And what it will return is a log likelihood, that's sum of the values. And if I want to, if I now R has this other feature that I'm not going to teach you guys about how to use. Some of you know what I'm about to do, particularly if you work with me in my lab. But if you put the word browser in here, a browser function, and then you put that re uh, rerun the code for the function, saving it into the R environment. Now, when I run this, it actually pauses the execution of R as if we're in the function itself. So now, when you look at what's happening in the function, the environment down here no longer says global, right? That was where we were before. Global contains everything. It is what's called a child environment, right? It's a separate little subset of global, and it only has mean, standard deviation, and x. So that's all it has to work with. Right now, if I type a value in, like mean, it'll show up in here. These values are sort of promised to the function as they come in. But then what you can see is this dnorm function, it evaluates the log likelihood for each individual observation for their given value of x went for a given mean of 10 and the standard deviation of 1. Right? So far, so good. And then the sum just is the sum of all that. Oops. And then we return it as it goes. So a function in R, for some of your life, functions are easy. And if you're like, again, I say this about Lisa Hoffman, uh, I try to teach her some functions and she starts using them everywhere. So some of you take Lisa's classes and you see functions in her code. That's since our conversation earlier this year. Not that I'm going to take credit. I give her little breadcrumbs and I'm like, you're on your own because, well, I got my own stuff to screw up, right? So if you want to know more about it, there's a book called Advanced R by Hadley Wickham. Um, this online book, it's free. If you, this is the website right here, or if you just type Advanced R Hadley, but in that book itself has a section on functions. This is not a very long chapter, and I would encourage each of you to try to read it to get a sense. It's a very high level overview of how functions work in R, and I think it's really helpful. But again, what I just showed you should get you to build a function. Did that answer your question, Kendra? Awesome. Other questions from other people on this subject? Negative. No questions. Okay, let me go to the next question of homework. The next part of homework asks you to use the optim function in R to maximize the log likelihood. Now, this is where I was expecting you to go to R and type in help optim. Optim describes how to use basically a function, and it will figure out an optimal value, in this case, a maximum or a minimum, which is cool, right? Because that's what we can use for maximum likelihood. So here for optim, if I type optim here, let's imagine I want to maximize my normal sample here. So if I say, um, I'll call it result, I'll just do optim. Optim. So how it works is this: par is the initial values of parameters to be optimized over. All right. So in our case, we have two, the mean and the standard deviation. And so we tell it par, and we have to give it a starting guess. So par, here it wants me to guess with 0 and 1. So why not? We'll try that. The mean of 0, standard deviation of 1. Standard deviation is right on. The mean of 0 is not, right? Fn is the function we'd like to use. So basically, it will submit these two values as the first two arguments to that function, and then use the function and try to figure out which it'll change the entries in the first two values such that it tries to detect where the maximum value would be for the likelihood itself. So here, that's what log likelihood, that's the function that comes out. There's also x, which is our additional data. That's the other argument we need to send to the function here. So when I run optim, oh, I have browser enabled. That's not good. It will pause every time it uses the function. Optim here, oops, maybe I messed this up. Let me see. Of course, now you get to see me go live into this as well too. Let's see. This is where my live example starts to fail. Functions. Okay, getting there. Give me a moment here. Yes, Vladimir, you've solved this. What am I doing wrong here? Gotcha. That's it. Here we go. Params, we'll call it, and mean equals params 1, the first element, and SD equals params 2. So there we have it. And now it starts to work, but things are going to be a little weird because we have a couple things we have to consider. One is that, thank you for that, Vladimir. I'm sorry, I totally whiffed on that. One is, first of all, it says here, it's by default performing minimization. So what we really need to do is change this FN scale to negative, and that makes me laugh because it's like, why don't you work, you effing scale? But anyway, that right there is what we need to put in. That will maximize the likelihood. So here, that worked. It gave us a value of negative 147.4114 or 4004 with a value of the mean of 9.99, a value of standard deviation of 1.05. And if you want to compare that with our data, we could say mean of x is 9.99. So that worked. And standard deviation of x. Now, we have a little bit of an issue with standard deviation of x. It's 1.06. Why is our sample standard deviation bigger than our MLE? Anybody want to mention why? What if I told you our sample standard deviation uses n minus 1? So this would be, let's see here. And MLE uses n. So if I multiply by n minus 1, then divide by n to change its denominator, we end up getting a result. Actually, this is, we need to do this on the variance side because it's under the radical otherwise. That, all this goes into square root, and there's our number. That should be our MLE, and sure enough, it's pretty close to that. Now, a couple other notes on this. NANs are being produced, and that's because there's nothing about how I just did this optimization that puts a boundary on the standard deviation. You can leave it like this. It still works for this problem. I don't need you to become an expert at Optim. It's more the idea. But as you might be able to tell here, there are options for lower and upper. And so it says, if we use the method Brent, then our options could be a set of bounds for the variables. And I can't believe I'm going to try this, but I'm going to try it. We'll make this Brent for the method. And then the lower is that. The lower bound is negative infinity for the mean. And then our second parameter is the standard deviation, which is 0. And if we rerun that, oh, not available. Oh, no, I need this one right here. Nope. Never mind. All right. That's not going to work. Anyway, there are ways of doing it. I know one of you at least has gotten that taken care of. I don't expect it, but that's Optim. And this process repeats itself if you have built this same function for the Bernoulli. Questions on Optim? If you're wondering why you're made to do this, let me tell you again, you'll never know when you need to use an optimizer, particularly if you keep getting further and further in statistics, because not everything is in a package given to you by somebody else. Turns out the people building the packages are doing this type of stuff too. So you have the skills to do this as well. But that's my motivation for you. Other questions on this part 3 using Optim at all? No questions. All right. Part 4, visualization. This is, I didn't realize this might be a little harder than it needs to be. So I'm going to say you may not need to do um, the first part, the log likelihood across iterations. There's a control feature that you can plot. There's a control feature that you can have Optim tell you more information. Let me see if I can find the details here. Trace. There it is. Try this. Trace. That's it. There it is. This right here is telling you what's happening under the algorithm itself. And these are values, I believe. Yes, this is the value of the log likelihood it's optimizing. So what I was thinking about is having you plot that. I don't necessarily need that. It's hard to get this object to come out of Optim, so it doesn't necessarily need to be there. But for the Bernoulli distribution, this is a plot you can make on your own. Think of it this way. This distribution, we want pi, the parameter value, to be on the x-axis, right, between 0 and 1. And on the y-axis, I want the value of the log likelihood. And that would come from taking basically a loop over values of pi and calculating the log likelihood for each one of those values that you submit to it. And that'll give you a shape of what the log likelihood is. And what you should see is the maximum should be roughly about, in the log likelihood, should be roughly where pi is that gives you the result from Optim. Everybody following? Probably not. All right. Sounds like you're following. No questions. Questions? Let me pause. Questions. Formally, questions. Yep. Yeah, here, let me give you an example. Um, All right, I'm going to loop through values of the mean here for x. Condition. I'll keep the standard deviation 1, and we'll build it that way. Okay. So first of all, pick values of the mean. I'm going to put a sequence of values between -8 and 12 in zero point 0.1 increments. So this right here, I'm going to try each one of these. Actually, not -8, +8 and 12, and I'll make it 0.01 because I'm crazy. So each one of these values, I'm going to test out and calculate a log likelihood. Okay. So simply, I'm going to create LL values as a null object to save the values that I want. I'm going to say for mean in 1 through length mean values. I'm going to then calculate the log likelihood for the mean, giving this also the normal log likelihood, also the standard deviation of 1, right? And at the end of this, now I have a vector of log likelihood values for each value of that mean. So now what I'm looking to plot is on the x-axis, the mean values. On the y-axis, the log likelihood values. And the type of plot I'm going to make as a line plot. So this is telling you, for instance, what the log likelihood value is. Now you can only, I mean, technically we could have done 2 dimensions here. I don't have that syntax off the top of my head, so I'm not asking you to do that. But basically saying, for the standard deviation of 1, the maximum likelihood estimate for our data should be somewhere around 10. That's where the peak of the curve is. This is what I'm looking for. Instead of having a mean down here that's between, a positive real or any real number, this is going to be a decimal value between 0 and 1 because that's how the mean of Bernoulli works. Does that answer your question, Vladimir? Other questions on that? Okay. So at that point, the rest of it is sort of reflecting on what you did, reflect away. You know how to do that, and then how to return. So that's homework. How are we doing with questions? I think it's a bit of a challenging assignment, but I think it's a good one. And this is an upper level graduate class, so I'm hoping to challenge you a bit as well too. I will tell you that the students where I've trained them on this have tended to manage advanced statistics much better. I feel like understanding how log likelihoods work is a fundamental thing for running likelihood-based analyses. And hopefully this will help you as well too. But maybe you already know already. Who knows? Okay, we got 10 minutes till break time. Should we start on lecture or does anybody have any questions? Okay, I think that means start on lecture. Let's do that. All right. So I created this markdown document, Quarto markdown document, that has all of our lecture today. And I could walk through it. I'm going to walk through it. I'm also going to walk through the R code on the side as well too. But I'll start with the handout itself. I warn you that I'm not good at teaching from handouts, so this is sort of, I like to have slides to help focus me. So we'll see how this goes. If you've got tips, let me know. Um, but here's what we're going to do. So a couple weeks ago, when we had class last, I started to get into what Lavon does, and I did a little bit. And everybody seems to have at least a basic background of Lavon. I'm going to keep not going to go deeper into Lavon. I'm going to just use it like we know how to use it and give examples in Lavon. Our goal is this. What we're working toward is building. There's two versions, two things I'm going to try to accomplish with this. Number one, I'm going to try to accomplish taking Lavon and showing you that it has likelihood-based features, and so try to recreate the log likelihood at first with the multivariate normal distribution to show you how this is working, mainly because I want to tie it to that part of our lecture before too. And then second, we're going to go and take missing data and start showing how missing data works in Lavon in multiple ways. And it's sort of like, to me, the end of chapter 3 looked a lot like, I don't know, like a model soup. Like there's not this model and that model and this model. And I'm trying to cut through that a little bit more evenly. And I'm hopeful that this will happen. I think there's still a lot of this model, that model, this model here, but I'll narrate as I go. Are we good? Shall I start? All right. Last time I mentioned these data, I have this example from a paper from Pajares and Miller. I don't know that I even left the reference in here. So I'm generating random data based on the paper, but then I'm going to make the data missing, right? So I generated complete data, and I want to just introduce missingness in how I'm doing this, because how I'm generating missing data here follows the missing at random assumption. So here's the thing. I have this data set. I have a bunch of outcome variables. Let's see, what are their names? Here they are. Whether a person was a female, the number of high school math classes they took, the college credit hours in math classes they took, a person's perceived usefulness of mathematics, how they perceive whether math is useful or not, kind of like me trying to tell you that maximum likelihood is really useful. This is your perception of that. Um, Math self-concept that sort of describes how good you are, how you feel, how good you feel about your own ability to do math. I don't know what MAS is. I've forgotten that. I'll have to look that one up. But math self-efficacy and performance. So basically, performance is the number of questions right on a 20-item test. I generated it as normal because that's how the analysis worked. And I'm going to introduce some missing data. Math anxiety. Thank you, Vladimir. Math anxiety. Are you scared of math? Uh, Math self-concept and math self-efficacy. I'm not sure how they differ. I'm not a math ed expert, but there we go. So to generate missing data, I first started with introducing a model to predict which observations are missing. And the what we're using for our example analysis today, at least to start, is what we're trying to predict is whether or not um, college credit predicts how you perform in math, how college credit predicts how much you perceive usefulness in math. And then it's not just college credit predicting both those outcomes, but also female, whether a person was a male or a female. And then on top of that, an interaction as well, too, between college credit and the sex, biological sex of an individual as specified here. So to do this, I have to introduce missing. And I want those values, I'm going to make sure that CC, performance, and usefulness are missing, but they're going to be related to other values in the data set, thereby mating the missing at random assumption. So what I created for this was a logistic regression. And that logistic regression, I fixed some values of parameters. Now, why I picked these numbers was because it gave me a nice rounded blend of what was missing versus what was not. If I changed some of these, a lot became more missing. So this was sort of a normal approach, guess and check. I don't have any rationale for it, but the key thing is they're related. So this logistic regression in this process, if I go up to this on my slide, my R file here, let me switch over to this and show you how it works. Um, Here, the logistic regression basically says the probability any observation is missing is a function of an intercept, the status of their biological sex, math self-confidence, confidence, math anxiety, and math self-efficacy. And each of these is the regression slope on a logit scale for each of those variables. So now, if you look at this, for all of my data, depending on what they have, I actually have the log odds of the observation being missing conditional it on the other values in the data set. I can then change that into a probability right here. And that tells you the probability any one observation is missing based on my data, based on the other values. And then with that probability, I sample a random uniform number. If it's less than the probability, uh, it's the data become missing, and if it's more than it, they stay the same. The question in the chat is, which file is this in? This is in the GitHub repo file. Let me show you how to get to it. Go to our repository, missing data methods. This is our syllabus, and if you click on our files, this will be the file that is MLE with missing data. This one right here is that file. The file that has my handout that I'm showing on the other side of the screen is this QMD file, and then the handout itself is missing data. This miss HTML. Thank you. Okay, so we come back here. Now I can tell you these are the probabilities. Let's go and see which ones we need to make missing. When we do that, these are the missing values, and I make them NA. And now I have missing data on college credit. Cool? You can see where I'm going with this. I had you last week put a model into our miniature reading assessment. Eventually, you're going to create data with your model, and then you're going to make the data missing. That's where our next steps are going to be. But this is sort of a process that we're going through. All right. I do the same thing for each three variables. Each one has a separate function. I'm going to just run all that code and skip up to the front to where we can now talk about missing data, since we're just about to break. And this full data frame, data O2, looks like this. You'll see the variables that have missing values are CC, usefulness, and performance. Those were the three that we've created missing on. And those are all three that are going to be in an analysis that we're about to do. And I want to show you how that analysis works with Lavon with certain variations of how we put variables in and what it does to the log likelihood function itself. Basically, we need Lavon to treat all the data we have as observed and not omit any case, right? But anything that's missing, we need its likelihood function to be adjusted so that missing data is omitted, but every other piece of data is maintained. That makes sense? All right. And going back to the handout, again, I have 1 minute till break, but I'm just going to say this next part. Here's some data exploration. Here's the density or the distribution of college credit hours. And you'll see this is simulated data because it goes below zero. Someone has negative credit hours in math, probably not good. But by the way, the analysis these folks ran, of course, it was 1994, so 30 years ago. That's the assumption it has of the data. And these were numbers from their paper, so tells you whether or not that's appropriate. I also centered the values of CC by its mean, so CC minus 10 is here. And we could create an interaction term, but we'll do that later on. We'll need this later on. Basically, female by CC10 is the product of female times CC10 itself. I then stick all of these variables into a new data file just for this analysis itself. We'll come back to the full data analysis later on, but most of this lecture will be based on just these four variables: performance, perceived usefulness, biological sex, and CC10. Okay? On that note, we're going to pause. I think, is that like a radio tease, a podcast tease? When we come back, we'll see what we do with our missing data. So come back in 10 minutes. I'll see you at 1:30. Sound good? I'm not going to quit my day job. I may get fired from my day job, but I'm not going to quit it and just start in radio. Let's put it that way. All right. I'll be back in 10 minutes. I'll have the screen off if I'm not at my desk, but once I come back, I'll put my screen, my video and audio on. So see you just a bit. And break is over, just like that. Are you ready to see the exciting cliffhanger? What happens with missing data in Lavon? You probably already know a little bit of it, but we're going to continue on and fully investigate it. So I have all my data here, and I wanted to talk about first, I created this new data file that just has these four observations. None should be missing on all, right? So I have nobody is missing on everything, which is good. I mentioned that because, yes, you can have missing, if you have missing data on all, and those are the only variables in your analysis, you have no data on a person. It's like you didn't observe a person at all, right? So that's sort of one of our thought points there. Let me bring back my presentation and get to the part where we're here. So we're going to start with an empty model. An empty model is simply, you've seen them before. In fact, Lisa starts with them, and if you took Lisa for intermediate or generalized, we almost always start with an empty model. It's a really nice accounting trick, tells you how much variance is what you're doing. But we're just going to estimate, we're going to take our two outcomes, performance and usefulness, and predict them without predictors whatsoever. But we're doing this because we need to know how much data we have and to see what happens to our analyses. So here, one thing I wanted to check, I'm looking to see if somebody is missing on both performance and date and usefulness. And we see there are 12 observations that are missing on both. So what that should tell us is, in this analysis, if we look at our syntax, I'm using the Lavon function to estimate this code, which means I have to specify every parameter I have. And I'm using that function explicitly in this class because I want you to be thinking about which parameters are and how this builds. We're first going to understand, number one, that MEM+ uses, without, by default, assumes data following a multivariate normal distribution. So with two variables, that means we have 5 parameters, right? It's a bivariate normal distribution. We talked about multivariate normal a couple weeks ago. There are 2 means, and we have to define them in Lavon syntax. The tilde 1 defines a mean. Tilde is a regression command, and 1 is the part of R's regression formula syntax to talk about the intercept. So that's really what's happening here. This is like a regression with no predictors, just estimating an intercept. Excuse me. Now, we also have to describe variance. We have 2 variances, the variance of performance and the variance of usefulness. Lavon's code for variance is a double tilde, right? Technically, that code also applies to covariance. But the covariance of a variable with itself is its variance, right? Does that make sense? So perf double tilde perf is the covariance of perf with perf, which is its variance. Finally, the covariance perf double tilde use, that appears as well. I will note that you could put use on this perf line with a plus by it, and it would estimate the same, but I'm doing this to be very explicit as to what's a mean, what's a variance with a covariance, because I'm trying to tie multivariate normal, the distribution from theory, to what we're getting in Lavon. So that's our Lavon syntax. Any questions on that? Okay. So now, when I go and estimate the model in Lavon, I use this command right here. I give it the syntax. I tell it our data frame. Actually, this data frame should have been the new data, but that's okay. Data O2 works. It's the same data. I'm using the MLR estimator. That stands for robust maximum likelihood. Craig Enders talks about that in his book. That helps us have protection against lepto or platykurtic data. And then finally, mimic equals M plus. Now, you don't have to use this, but using it, I'm used to M plus, and a lot of you will use M plus versus Lavon. So keeping mimic equals M plus keeps things similar. With respect to missing data, that means specifically, if we have a predictor in our model, the predictor will not automatically become part of the maximum likelihood algorithm. Basically, we treat the predictor as not being part of it at all. If we turn this off, by default, that predictor now becomes part of the algorithm. So there's 2 visions for this, right? From a missing data point of view, having more predictors in the algorithm is how we get missing data protection. That's important. But the distribution it assumes by putting it into the algorithm is that it's also normally distributed. And we know for a fact that when we put in the female variable, which is 0 and 1, an indicator of whether the sex of a person is a female, we know that's not going to be normally distributed because it's binary. So I like M plus's strategy where it just sort of does not assume any distribution for the predictors. And I'm going to keep this in here for that purpose. That's why I have it there. But just remember, if you take that off, you now have to decide whether your predictors are in the likelihood function or not. And if they are in the likelihood function and the likelihood's not the right one for your data, that's a problem. Cool? All right. So, turns out we ran the Lavon and it tells us, hey, some cases are empty and will be ignored. That's your warning that it is removing cases. But we knew ahead of time that we had 12 cases that should be removed because they had no data on any of them. And what we can find from the top of the Lavon output is right here. We have 338 observations that we use out of 350 total. So that's 12. That's what we want it to be. And again, I'm being very slow and pedantic about this part because this is your key to understanding if your analysis is using the data, maximum amount of data that we have. Okay? Okay. It also tells you the number of missing patterns. Here, I'm going to guess that our missing patterns are 3. Well, we ignored all the completely missing. So the missing patterns would be no missing at all. So both variables are observed. Missing on one or missing on the other. Those are the 3 patterns I think it's going to have with 2 variables. Okay? Now, what you should see here in terms of model fit, 0 means we have a saturated model. We're estimating all the parameters of the multivariate normal distribution that's implying. So we don't check for model fit, or we don't have a test for model fit. And what that means is This saturated model, the bit user model right here, should have a 0 for degrees of freedom and a 0 for the likelihood ratio test. What this section would normally do is fit the saturated multivariate normal model where all the parameters are estimated and compare that with a likelihood ratio test to your model where the number of degrees of freedom is the number of parameters different between the two models. So here, there's no difference. We have estimated the saturated model, so there's 0 difference in log likelihood, and there's 0 degrees of freedom. That also means some of the fit indices that I briefly mentioned the last time, CFI and TLI, are at their optimal values of 1, and RMSEA is at its optimal value of 0, and that we have no standardized root mean squared residual. Basically, we are recovering the full saturated multivariate normal distribution from this model. That's what it's saying. So model fit's not a big deal here. How are we doing? Sound good? Okay. Now we can see our parameter estimates here, right? We've got our covariance estimate to be 9.9. When I asked for it to give me a summary, I told it to turn on standardized estimates, and I'll tell you that for just a moment, in just a moment. And fit measures being true. Fit measures, again, is these model fit statistics up here, which will become increasingly important as we go on. And then standardized tells us standardized coefficients. We know perf double tilde use is a covariance. So that's the covariance between performance and usefulness. But remember, covariances have a weird scale. This is in units of performance by units of usefulness. Perf uses. I don't know what that is. But if you look over here, std.all, that tells you the standardized covariance. Turns out that's its correlation. So our correlation between variables is 0.209. That's how we see that there. That's one useful thing about standardization in this simple model. The rest of this is not really informative. Actually, we can start with variances. This is our variance of performance or variance of usefulness. The standardized version of variance just divides by that variable's variance, and it turns out standardized variance is 1. Hooray. And then, of course, we have our mean estimate of performance of 13.8 and our usefulness of 50.8. And the standardized estimates for means don't usually mean a whole lot, so we just leave those alone. Questions on any of the output from Model 1 so far? Okay, I'm going to start showing a few other Lavon pieces of information. Some of this is going to be very repetitive across the handout, but I'm putting it there in case sometimes you need to see it. The first thing we want is what the model says our mean vector and covariance matrix should be. Now, in this model, with our parameterization right here, we don't have to search for this. We are getting the mean vector and the covariance matrix. Then in other models, we're not going to have that. So I'm just going to tie the two together here. The mean vector is 13 and 50. Well, that's our estimates. Those are exactly our estimates. So we don't see anything changed. This is the lower triangle of the covariance matrix, right, that our model suggests. And you'll note that here, these are the estimates that are literally from our output. The diagonal of the covariance matrix is our variance, gives our variances, and the off diagonal gives our covariance. So that's what our model thinks our data should look like. That is what we call fitted, the fitted model, the fitted covariance matrix. Then we can actually look at the same data if we wanted to using R, right? Just to compare how close our MLEs are. And sure enough, here we go. Our mean vector from R is 13.842, whereas it 13.837 before. A little off. Usefulness is 50.802 in our estimate versus 50.61 in our mean vector as well. It can be a little off with the likelihood algorithm. Next, and the reason for that offness, by the way, is the fact that it's optimizing the variance, which is divided by n and not n minus 1. Here in the covariance matrix, we would see the diagonal is, again, a little bit different. The off diagonal is a little bit different as well, too. And again, this is using the n versus n minus 1. So if I convert them to divided by n, you'll see that they're a little bit closer to what Lavon gives, but not identical either. Now, interestingly, Lavon also can give you the sample statistics, and these are what Levon thinks our sample statistics are. They're a little bit different, and that's because the difference in the likelihood versus just using the straight formula as well, particularly with missing data. And then finally, residuals. I think we mentioned this a little bit before. This is the difference between what our model thinks these values are, the mean vector and covariance matrix, and what is in our data, and these are zero. So again, what does zero mean? Zero means saturated, means we've perfectly described our data. That's ideal, and that's going to be super ideal once we get to adding auxiliary variables to an analysis as well. Right. So one of the things you can always do to check whether or not you saturated the right number of parameters in your model is take a look at the residual matrices and the parameters, the variables that you don't care about, not care about, the auxiliary variables or otherwise, should see zeros there for those parts of the matrices. How are we doing so far? Okay. We also could take these raw residuals and make them normalized. In this class, it's less important, but in some classes, particularly in path analysis, the size of the residual may not be indicative as to whether or not you are far off from it. Because in a covariance matrix, remember, the size of the values is governed by the size of the diagonal. Right? The bigger the diagonal, the bigger the off diagonal can be. So it's not easy to tell whether a large raw residual is meaningfully large because the scale of the actual variables themselves, the variances decide that. So to put them on a common metric, there's a normalized residual. Again, we don't have any because we have no residuals at all. We perfectly fit the model, but that's where normalized comes in. And then our R squared values. If you wanted to know what R squared is here, we should see a zero R squared because we're not predicting anything. And that's right, what we have. Okay, so there's our first model with Levon. How are we doing? You want to see the path diagram? Let R draw it. There it is. We have usefulness, that's observed. Performance, that's observed. The double-headed arrow between them reflects that this is a covariance. If there was only one arrow on it, it would be a prediction relationship, right? Usefulness conditional on performance or vice versa. And then this little double-headed loop right here says that's a variance that we're estimating. Not shown on this graph is a place for the means. Mean structure, and I hate the mean structured graphs, but they're not there either. But path diagram is okay somewhat. And we can also overlay numbers on top of that. That's what this does here. Okay, questions on any of this? Still none. All right, now I want to verify the likelihood for you. Shall we do that? Why I do that is, again, connecting the theory in class to the practice in what's going on in Levon. And here, if I go down to the end over here, let me run up to that part. What I'm going to do is I'm going to go through each of the each of the values of the data for each observation, and I'm going to calculate the multivariate normal log likelihood. Now I'm using a function called DVM. Excuse me, can't even read. DMV norm. DMV norm is part of which package is that? This is part of the MVT norm package, but you will note that there are thousands of multivariate normal likelihood functions out there. You can probably find them in almost every package. That's how common this is. It takes a vector of data for each person, and then our mean vector and our covariance matrix. And so here, I'm only taking the complete data. I'm starting with a value for a placeholder for log likelihood for each person, and I wanted to walk down and grab each person's data. Whoops. I do obs equals 1. I have the first person's data right here, two values. These are the variables that they gave me. And I'm keeping the variables they gave me because as I use DMV norm, remember there are three different types of patterns of data. One is where we've observed both variables. One is where we've only observed one, and one is where we've observed the other, right? So here, this is a way that I can trick R to knowing that the multivariate normal for sometimes should be 2 dimensions if it gave us both pieces of data, or it should be 1 dimension if they give us one of the other variables. Okay? So for this first observation right here, our log likelihood, whoops, is negative 6.85. So it just plugs in both values. Now I wanted to take a glance at what happens if we get to like our third observation. This person does not have a score for performance, but does have a score for usefulness. Let's see what happens to their data as well. So here, this is observation 3 now. Our observed data is just a vector that says performance and usefulness here. The observed variables is just usefulness, right? So what I'm inputting into R is just the variable I saw, usefulness, and then just the mean for that variable that I saw, that's the mean of usefulness, and then just the variance of that variable as well, okay? So now this multivariate normal has one dimension, not two. There's really a univariate normal here. And in that case, I can still use the functions as I did before, and it's going to give me a value of negative 4.38. And that's the part of maximum likelihood I really wanted to get expressed to you. And I'm going to run it for everybody. What you can see here is that everybody has a log likelihood. Everybody. Some of those log likelihoods are bigger than others, and some of them reflect people who have only given us one piece of data instead of two. But that is how it built. That's how the likelihood function works. And that's what a maximum likelihood is doing behind the scenes, is that if a person only has one observed variable, likelihood function shifts from two dimensions to one. But it's still normal, still maximum likelihood. And if I calculate the sum, I get a value of negative 1829.344. And if I compare that with Lavon, you can see that we're really close. It's a bit of rounding error. That rounding error is coming because my mean vector and covariance matrix weren't exactly what Lavon's were. But that's how it's working. So, and if you don't believe me, just go up to the top here. There's the Lavon log likelihood, negative 18.29062. And if I go back down, we're really close to that. So what I'm hoping that this shows you is the things I'm talking about in class are running behind the scene in Lavon. That's building it. But more importantly, what's happening for us for missing data is that for both of these variables, we should have an analysis here that allows us to mostly assume missing at random for our data. And I say mostly. That's because we have 338 out of 350 observations. So we're almost there. Really, to make it all protection against missing at random, we'd need somehow to get all 350 observations into the likelihood. But for just two variables, we can't do that because if we only restrict ourselves to these two variables, there are 12 people who did not give us either. So that motivates the need to put other variables into analysis. That's what we're trying to do next. Questions on any of this? How's this sitting? Does it make sense mostly? Okay. If it doesn't, I'm happy to answer any questions you have. Let me move to this part here. Okay, the other thing I wanted to show you is, and this is easier to show with two variables than it is when we get to lots. But pretty soon, we're going to move into a spot where we need this approach for missing data called factored regressions. The idea of factored regression is based on, hang on here. Let me get to the spot where I want here, comparing factored regressions. So the idea is this, right now, what would happen if we said that our previous model did this? It basically looked at the likelihood function of performance and usefulness together, use that and optimized Lavon to figure out the maximum of the parameters it needed. But remember from several weeks ago, the properties of conditional distributions, right? This joint distribution, so joint distribution, the distribution of more than one variable, can be factored into a conditional distribution times a marginal distribution, right? And in this first sense, we're going to take performance and make it conditional on usefulness. So this is really going to be, so what that implies It's just like in R, this would imply that we're doing a linear regression predicting usefulness or performance from usefulness. And that's what it really shows up. And then we need to multiply that by a function of the marginal distribution of usefulness itself. This approach should give us an equivalent model. However, the parameters themselves will be different because now they're a series of regression coefficients for the performance and a univariate normal set of parameters for usefulness. Does this make sense what I'm doing? Right? I'm replacing a joint distribution with the product of a conditional times a marginal. Why do you think I would want to do that in the big picture? I'm not motivating why yet, but I'm sort of hinting at it. What do you think? Yes. Yes, that would be one answer. So the answer was we don't have to necessarily assume multivariate normal distribution. That's correct, right? In our example for this with usefulness and performance, you saw that I generated from a multivariate normal. So this is okay. But when we get female, that's going to be a problem, right? And female is going to be a problem because if we wanted to look at the joint distribution of performance and female, let's say, there is no joint distribution that's easily specified for a pair of variables where one is continuous and one is discrete. When I say easily, I mean go search Wikipedia for the Cauchy distribution like we did earlier in class. That worked. There is no alternative to that easily. So instead, what we say is, oh, well, I need this joint distribution because I need to have both variables in the likelihood function, but I'm only going to arrive at it not through putting the both variables in, but by conditioning on distributions that I know how to do. So for instance, performance conditional on female is a simple linear regression where female predicts performance. But then the distribution of female marginally doesn't have to be univariate normal, although in Levon it would be, but it could be Bernoulli. And then the two of them combined can give us a joint distribution that is proper and protects for missing data. That's the goal. Does that make sense? I don't know if it makes sense. Great. So what I'm doing here is setting up what's going to happen when we have variables that are clearly not normal. What are variables that are clearly not normal? Discrete variables, interaction terms, quadratic terms. All of those things are not going to follow a normal distribution necessarily. So this is setting up an alternate approach, but showing you how it works with the pair of variables, because with the pair of variables, this really is easier to see. Okay? All right, so the code for this, syntax from Levon. Remember the distinction between exogenous variables and endogenous variables. Now, because both variables, actually, back in this scenario here, our first model, we only had, well, it's hard to tell. Neither of these variables are predicted by anything. So are they exogenous? Are they endogenous? Eh. Right? An endogenous variable is one that's predicted by the model. An exogenous variable is one that's sort of described by a model but not necessarily predicted. I could make a case where these were probably exogenous variables before. Right? There's nothing predicting them. But now, once we get into the factored regression approach, you'll note that performance being predicted by usefulness is what we call an endogenous variable, meaning it's being its variance is being explained, and usefulness is now an exogenous variable, meaning we're going to have it in the likelihood, but we're not going to explain its variance. So I separated my syntax by exogenous versus endogenous. Let's start with usefulness. The mean of usefulness we go and specify, and the variance we specify. But we don't have a covariance between performance and usefulness, right? Because usefulness is the only exogenous variable that we have. Next, we need to specify the regression, the conditional distribution of performance given usefulness. And we do that within R-like bit of syntax. Performance tilde 1 plus usefulness. This basically says we're predicting performance. There will be an intercept and a slope for usefulness. That slope takes the place of the covariance, right? In fact, if we tried to estimate the covariance between usefulness and performance and the slope, things won't go well because they're effectively the same parameter with a different, like a transformation effectively. So put that in. We also need the residual variance of performance. Now remember, this is now a residual variance because it's what is left over in performance after explaining it with usefulness. Does that make sense? Okay. So if we estimate our model, again, most of this is the same with the exception of the syntax being different. Again, we still have 12 cases that are omitted because they're empty. So we haven't changed anything about our missing data. This doesn't change. Our model is not going to be much different with this than it is the previous time. Furthermore, if we go on down here, you'll note, I don't know if you remember, but before I calculated this log likelihood. You can go back, go on YouTube, hit rewind, find it, or I guess I could scroll up, but I'm going to lose the number. That's the same number of log likelihood as the model before. And that brings up something I want to talk about, which is a model that has the same number of parameters and the same log likelihood. When you have a pair of models that have the same number of parameters, same log likelihood, they're equivalent models. They may be parameterized slightly differently, but they're equivalent. And here, you can tell we have 5 parameters. Our model fits perfect, and our log likelihood is identical to our previous model. Does that make sense? All right. So we go on to our parameters. Now, usefulness has a slope of 0.36. It's significant, whatever that means. Um, but the correlation parameter, the standardized version of it, is still the value that we saw previously. So standardized regression slope is also correlation. Hey, how about that? We have our intercepts. Now, usefulness is no longer an intercept. Remember, that's a mean, but performance is an intercept, and that's different than before, right? The mean of performance that we saw before, we found it to be, where did it go? 13.837. But now we see an intercept for performance that's 12.008. And that's because when we specify the factored version of the model, this intercept reflects the value of performance when usefulness is equal to 0. Right? So it's now conditional on the value of usefulness. So the parameters have changed, but the model is the same. Sure enough, we can go use that and get back to our parameters. I'll do that in just a bit here. Finally, our variance estimates, right? We have our residual, our variance estimate of usefulness, not a residual, but a variance. But our variance estimate of performance is 7.822. You'll note that that's not the same as we had before. Our variance performance before happened to be 8.60. That difference is because this is not a variance, it's a residual variance. So we've explained some of the variance performance with some of the variance in usefulness. Right? How are we doing with all that? And I'll show a combination in just a bit. But that's one way we could factor it. Right? So what I've just told you is model 1, where both variables were not being predicted, but were endogenous, right? Is equivalent to model 2, where performance is being predicted by usefulness, and usefulness is entered as a univariate normal. Well, it turns out that's a very directional relationship. Math don't care what the direction is. Math doesn't care a lot. The cold, hard facts of logic are, to me, very refreshing, but sometimes very sterile. We literally can go and turn this around to this way. We could say, let's predict usefulness with performance, not performance with usefulness, and see what happens. What's going to happen? How many of you think this is equivalent to the other two models? It should be, right? So what we should see is this model is identical to the other two as well, too. Right? So here, same setup. Exogenous mean is now performance instead of usefulness. Yes, I see a question. Oh, okay, gotcha. Our regression has usefulness now is predicted by an intercept in performance, and we have residual variance of usefulness. Again, we see we have 338 cases. We have 0 degrees of freedom. We should see the log likelihood is the same. Check, check, check. All three models have the same log likelihood, so they should be equivalent. And then our results are formatted a bit differently, right? The slope is 1.211, with the our standardized estimate being our correlation again. And you see these values. So it turns out all three of these models are the same. You can go back and calculate the non-standardized versions of what you have and figure out like your multivariate normal specifics. But I'm going to ask you a question. Let's imagine one of you says your performance on a test predicts or causes how well you believe math is useful. Basically, if you're better at doing math, you believe math is more useful. And then one of you says, no, it's the other way around. How well you believe math is useful, how much you believe math is useful will make your performance better, or usefulness causes performance. And then there's a third one of you who says, no. They just happen to covary together. Looking at these results, which one of you is right? They're equivalent. No one's right. And that's the part I want to mention. In this type of scenario, with this type of approach, what we're after is that joint distribution. Where did I put it? Right here. Right? And so this is equivalent to perf given use, but it's also equal to the opposite. So this is a situation in mathematics, again, running into the cold hard reality of the logic of the situation, is that there's no way to determine which one of these models is the most appropriate because they're all equivalent. And so if one of you says the relationship is usefulness causes performance, cool. And then someone says, wait a minute, no, it's performance causing usefulness. It's also cool. Turns out this data isn't going to shed light into which one of you is right. So when you have a big giant path model, it's one of the things we always talk about is turns out what you put in paths between the variables. And actually, I do have a path model here, right? I started with this one where we said, yeah, we're not describing anything. And then I changed it to where performance predicted usefulness, and then vice versa, usefulness predicted performance. There's three different path diagrams I could have drawn. Each of them has a very different way of saying how the causal order of the world works, but all three are equivalent. That's bad. Not bad. That's how it works. And then it's up to you to figure out a different way of experimenting or otherwise to see if you want to test a hypothesis that could be the relationship could be switched. But this is true for most path diagrams. So if you use a path diagram to describe a complex multivariate model and you switch one of the paths to be covariance to direct effect like a regression, model's going to fit equivalent. Okay, how are we doing? All right, let's see what happens then when we add predictors as main effects, right? So that was our model with just the two outcomes, performance and usefulness, but let's add female and CC10 and see if we can't predict performance and usefulness with each. So now we're going to specify the model syntax a little bit differently. Here, this could be called regressions, really. These are conditional means. So performance is being predicted by an intercept and by female and CC10. Usefulness is being predicted by intercept, female, and CC10. And you'll note in this syntax, even though the right-hand side after the tilde is the same, that does not mean that the parameters are equal, right? It's like doing two separate regression analyses simultaneously, right? Here, one of them will have its own set of parameters. Another one will have its own set of parameters. That's important because usefulness and performance are not on the same scale. They don't have the same mean. They don't have the same variance. Now, we'll also have residual variances for performance and usefulness. And we'll also have a residual covariance between the two. So now what we've done is basically made this a conditional multivariate normal distribution, where the two variables that are in the likelihood function, again, are performance and usefulness. But because we haven't specified female or CC10 anywhere except as acting on this regression, both of those are going to be left outside of the likelihood altogether. That's how this is working. How's that work for you? Any questions on this syntax or what I'm talking about here? Probably not. Okay, so we estimate our model. Again, all we've changed is just the model o2.syntax. And now we get a new warning. 105 cases were deleted due to missing values in exogenous variables, while fixed.x equals true. Well, it turns out fixed.x equals true comes from this mimic equals m plus part. So we've turned off the ability for this algorithm to enter female and CC10 into the likelihood. So it's not putting exogenous variables in the likelihood. I'm going to show you what happens when we do. Don't worry about that. But I wanted to talk about that for a second. If I turned off and mimic m equals m plus, turns out fixed.x becomes false. And now our likelihood function has 4 variables in it, not 2, female and CC10. And that causes a whole bunch of weirdness. Number one, it's not saturated, right? We still have to describe the distribution of female and CC10 jointly for it to be saturated. But number two, female is a binary variable. It can't be normally distributed. So those are two issues we're going to have to deal with. One we can deal with syntax, but the other, multivariate normal, will not change. I'm going to get to that in just a bit, but that's what's happening here. So how do you feel about this? We went from having only 12 cases excluded before to 105 excluded. We have a 350 in our sample. If I were to say to you, look, I use maximum likelihood, I'm good with missing data, I can assume missing at random, what would you tell me? Can I assume missing at random in this model? No, I cannot, because I'm omitting data, right? I have 105 cases due to missing values for either CC10 or female. And since I'm omitting that data, now I have potential to have a bias, particularly if that bias is related to anything in the model. So this is not, even though I'm using maximum likelihood, this is a situation where I'm not meeting fully the assumptions of missing at random. Is it that understanding coming through okay? Right. I'm trying to get you to think, and actually not just you thinking this for your data, when you review someone's manuscript, if you're a reviewer, not reviewer 2, of course, which used to be reviewer 3 when I started, but we needed fewer reviewers in our peer review. Reviewer 2 would know the difference here, and you need to be that reviewer. I know we always give reviewer 2 a bad name. Maybe you're reviewer 1, right? That's like saying, yeah, it's almost like a misleading claim. I'm using maximum likelihood, so I'm completely protected from missing data. That's not true. Just because you use maximum likelihood doesn't mean you can still have assumptions missing completely at random. Here, the key is you have to have every variable in the likelihood function for it to give you that protection and still have observations that are not omitted, right? So in analysis 1, we weren't fully missing at random either because we had 12 cases that were gone, right? Now we have 105 cases that were deleted. This is worse. Not getting better, but we're going to make it better in just a minute. How are we doing? Does it help for me to keep tying this to our missing data concepts? I hope so. Okay. Let's take a look. Yeah, 245 observations. However, take a look. When we see a test statistic of 0 with 0 degrees of freedom, what does that mean about our model in terms of parameters estimated to parameters possible to be estimated? It's saturated. So our model has every parameter estimated. That's good. So we do not need model fit. By the way, model test a baseline model. I've never liked that test. It compares our model to a multivariate normal where the variables are independent. That doesn't make any sense. It's kind of a joke of a test. I never look at it. We have a different log likelihood now, but that's because we're predicting these variables and their values are sort of residualized. And when we get to our parameter estimates, again, you'll see our regression coefficients for each. Now, you may be tempted to say these are the intercepts, or these are the means, but remember they're intercepts. That's why they're listed in the intercept section. This is the expected value of performance when female is 0, or otherwise a male is giving the test, and a person who has 10 credit hours of college credit. They would get 14 points, right? Turns out females are 1.5 points lower than males on this performance test for whatever reason. Right? Now we have residual variances. We can use that to calculate R squared. And finally, we have a residual covariance. Now, a residual covariance is an interesting term. If you had estimated both of these regressions separately using maximum likelihood, you may get very similar estimates depending on what data are missing versus which are not. But you wouldn't have a residual covariance. The residual covariance in a multivariate model helps. It helps basically describe how related you are in terms of how off you are predicting for both variables at once. And if you did this in a Bayesian sense, this almost is like saying, trying to describe whether residuals have like a prior distribution that may have some variation to it, right? If you know a little bit about how far you off on performance, tells you a little bit about how far you are off on usefulness. But let's go through and inspect a few more things. Here, when I ask it for the model predicted or model implied mean vector and covariance matrix, I get these values. It plugs in our exogenous values. And one of the other things that mimic equals m plus does is the numbers that you see. We did not estimate these parameters. We don't have a variance of CC10. We don't have a variance of female, and we do not have a covariance between the two of them. We did not estimate them, but the values plugged in are the values from the sample statistics. So here it runs sample statistics on those, and it plugs the values in as if we had estimated to saturate the covariance matrix. Same thing with the mean. We don't have an estimate from our model, but we could calculate a mean in our data, and that's what it's doing. So our residuals are back to 0. Our normalized residuals are 0. We don't have modification indices. Modification indices tell you which parameters to add to make things better. We don't have that. And then if we wanted the R square here, we could see that our R squared for performance was 0.111 and very little R squared for usefulness. And if we want a path diagram, here we have it. Or one with numbers, but no means. And of course, the numbers in the middle are right on top of each other, so that's my bad. So there's a way to fix that. I hope there's a way to fix that. I just didn't take the time to look for it. All right. What do you think so far? This analysis, not so good. Not because of the results, but because we got a bunch more missing data. Let's see what we can do about that. We're going to now take CC10 and put that into the likelihood function. Now, strategically, when I made missing data, I did not make missing data on the female variable. I did that strategically because if we somehow put CC10 back into the likelihood function, we don't need to worry about female being in the likelihood function. So we don't need to worry about this mismatch between female and multivariate normal. I'll show you what happens in that in another example, but show this here. So now what I've done is basically thought of this, it's almost like a factored regression approach, right? In fact, if I wanted to explain what I'm doing here, I actually have CC10 in our likelihood function. So now what we have is the joint distribution of performance and usefulness conditional on CC10. And then we have the marginal distribution of CC10. So if we factored this out, this next segment is basically this here. Performance and usefulness are still a multivariate normal distribution. CC10 is univariate normal, and their product gives us the joint distribution. Does that make sense to you? All right, let me put this in a different part of my slides. And I'll put this under example 3 right here. Right there. Okay. So that means we have to treat CC10 as an exogenous variable, estimate its mean, estimate its variance, and then the rest of the code is the same, right? We have our regression line for performance, our regression line for usefulness, residual variance of performance, residual variance of usefulness, and residual covariance itself. Now, question number one, is this model saturated with respect to all parameters? How many of you say yes? Don't stress. I see people thinking hard. I want you to think hard, but not stress about it. All right. How many people say no? I got a couple no's, 3 no's, 4 no's, 5 no's. Well, I'm gonna take a peek. Yeah, look at that. 1 degree of freedom. Where's that degree of freedom coming from? Let's find out. Let's see if we can find out, shall we? All right, here we go. We want it to be saturated. There's nothing about this that should make it not saturated. But let's see what happens. We have model fit now to worry about. With 1 degree of freedom, you will note that um, very easy to get good model fit with 1 degree of freedom. RMSEA is still 0. CFI and TLI is above 1. That can happen. It's always fun. But we can't tell exactly from this output where things are not saturated. Where we have to determine this is our model implied mean vector and covariance matrix. And here is where we see there's no relationship between female and CC10. And this is an interesting situation in Lavon because we said, hey, female shouldn't be part of the likelihood at all. But Lavon doesn't know what to do with that then. And this is why I wanted to show this to you. We want this to be saturated. It'd be better if it's fit would probably change very little if we added another parameter, but we have to add that covariance if we want this to be saturated. So what you'll see is we should have a residual. Yep, we have a bunch of residuals here, the raw residuals. Just by not having that value of the parameter there shifted all the other estimates. And this is the impact of model fit. If a model doesn't fit, it's usually because the model is trying to stretch to make a covariance matrix look like this when it really has a covariance matrix that looks like that. So all the terms are bending and being pulled in different ways. And even though we only have one parameter that's missing, we see our residuals show up everywhere now. Because even though we didn't saturate it with one parameter, now we have a problem, a little bit of a problem potentially. So, hey, we got to saturate it. But you know what? It's break time. So how about we take a 10-minute break and I leave that as the cliffhanger for you to come back at about 2:30 and we'll talk about that. Sound good? All right. Again, I will have the screen muted and my audio muted, and I'll put everything back on when we're getting ready to start again. So see you in 10 minutes. Thank you. All right, I'm going to do something dangerous. You know me, I love danger. Danger. Statistics with R. What's going to happen? Is my computer going to yell at me? Probably. I mentioned this is not a saturated model, and many of you said it wasn't saturated. You probably looked down and said, wait a minute, not saturated. There's a parameter there. And then we figured out which parameter it was. It was this one right here, female CC10. Can you saturate it? Can we saturate it? What do you think? What would you add to this model to saturate it? First of all, let me back up. Why would I want to have this model saturated? In our case, lack of saturation leads to residual values, particularly this use by female residual, that may bias our parameter estimates. And you think about what we've done, we haven't changed anything. Same model, we just added CC10 to the likelihood. But in doing that, we left out, we didn't know that Lavon was going to leave out a covariance. So with that left out, now the model has to sort of recalibrate itself, and the parameter estimates may be different from this model that's not saturated to the model that is. Now, I don't think they're going to be big, very large differences. But the key in building a model, particularly from this structural equation modeling, path modeling approach, is that if you have a bunch of observed data, there's nothing wrong with saturating your model. In fact, it's beneficial, right? We don't care that there would be a covariance between CC10 and female. We just need it to be in the model so that it allows our other parameters to be what they should be, the best they can. Because the more that we move from a saturated, from the more degrees of freedom there are in our model right here, the more likely it is that model misfit may cause our parameters to be biased. So why we need saturated to summarize? Model fit. A saturated model fits best. We want to stay there, particularly with observed variables as much as we can. Now, many of you are going to do latent variable analyses, psychometric models, and they'll never be saturated. But parts of the model could. And that's what I mean. So if you have auxiliary variables, you want those saturated, right? They should add to the analysis, but not detract from it or bias it. And by saturating them, they add but don't detract. So let's see here. That's question number one is why. Question number two is how. How would you change my code to saturate this model? The covariance between CC10 and female, and where would I put that? How about right there? Now, do you think it'll run? I haven't actually tested this, but I wanted to. Here I am again, living dangerously. Let's find out. Uh, uh, it ran, but it didn't converge, and it gave me the starting values. So you're thinking, wait a minute, that's not ideal either. Yeah, it's not. So the reason for that is we're in this weird spot. These types of models work best if sort of the endogenous, what's in the likelihood is either all or none. Meaning, if we put female in the likelihood, like this is trying to keep female out of the likelihood, but CC10 in, and then it doesn't know what to do to fill in the value of its covariance. Like if I were writing this code, I'd go to Levon and I'd just put the observed covariance in, but it defaults to the other direction. But fixing it's not going to be easy. So if female is out of the likelihood, we're not going to be able to fix this. So yet again, we're getting into a spot that this is less than an ideal analysis. Yeah, it's approximately right. But we can continue on and I'll show you what happens a little bit later. Does that sound okay? Okay, questions on any of this that I've done so far? Okay, so next, let's talk about missing data in the categorical variable. All right? I didn't create the categorical variable with missing data, but now I'm going to. Right? And female, I'm going to put missing data in. I'm actually going to just randomly pick values of female to make 0, NA. And you'll note that meets missing completely at random because there's nothing about the rest of the data that deal with it. So it's a really easy way to make missing data. Probably won't have much of an effect on the results, but I want to show you what happens when it goes forward. Okay? Okay. So now with missing data in model being female, you'll note that when I run that same model, now I get the warning again. 33 cases were deleted because missing values on female, because female's not in the likelihood. So to remedy that, we could add female to the likelihood function. Again, this is a bad idea, but it's a better idea than leaving it out altogether. Why is it a bad idea? Because putting it in the likelihood in Levon is going to make it treated as a normal distribution, and a binary variable can't have normal distribution. But we add it to the likelihood. Here we goes. Now we add female as a mean for the mean and the variance for exogenous, and there's our CC10 by female covariance. And then the rest of the model is the same. Now, how many of you think this is saturated? Meaning all parameters should be estimated. I do. Should be. Let's see what happens. It estimated just fine. It warned us that some observed variants are at least a factor 1,000 times larger than others. Yeah, that's because the variance of a binary variable is the mean times 1 minus the mean, or probability times 1 minus probability. So that variance is going to be between 0 and 1. And some of our variables have variances of 1,000. Yeah, that's going to happen. What happens when you stick that in the model? We look, hey, look, 0 degrees of freedom is 0 test statistic. That's saturated. Hooray. That's at least solved. Correct. Congrats. We can take a look at our information from our output now. Again, these are not big differences in parameters. I don't have the other parameters, but maybe I can go peek at them real quick. Just a second here. So these are the original parameters. And these are re-estimated parameters with female and the likelihood. And take a look at what happens. The slope for female on performance changes quite a bit, for instance. The slope for female on usefulness changes quite a bit. P-values don't change a whole lot. But now you'll see each of the other parameters and estimate it as well, too. So if we keep on moving down, we can see now our fitted covariance matrix does not have a 0 in any cell. That's where what saturated means. And we should see that these fit perfectly, and they do if we look at our residuals. We don't have any modification indices. There's no degrees of freedom left in our model. And now you can get an R squared. And there's our path diagram. Hooray! I always think that's funny. FML, isn't that a nice acronym instead of female? But yes. Okay, now I'm going to introduce to you. So this is the SEM approach that was talked about in the chapter. But let's go and think about this a little bit better using factorized or factored regression. Because the factored regression approach lays out a way that we could build a model, right? We want this joint distribution. We have missing data in all these variables. So we want this distribution right here. But we could factor it into a series of univariate regressions and calculate the likelihood function for each of those and come up with the joint likelihood overall, where this regression for female itself may be an empty model, but it uses a Bernoulli distribution. How are we doing? How's this class testing your patience? Because you're going to need a little more patience on this one. Now, I don't expect any of you to do this. In fact, once we get to Bayes, this gets a lot easier. But I'm going to show you, just in case any of you want to do this, how to do it. Okay? Now, I warn you, if you want to do this, it's going to be tough, but much respect, right? I don't know what that gets you. Plus, you'll have that feeling of accomplishment. Okay. So when I'm talking about factor regression here, it's a little bit different than the book. I'm conflating his factor regression in the book with an EM algorithm. Because what we have to really think about is once we have a likelihood function, we can use all sorts of functions to go and optimize it. The problem that we have in this situation with the binary variable is that we don't have a joint likelihood function to build without a factored regression. So factored regression is the tool to build the joint likelihood function using a series of functions that we know how to build. And then EM is what we're going to do to impute data with expected values and then calculate maximum likelihood estimates, iterating between the two of them throughout, which will arrive at the full solution. It's not perfect, and I don't expect you to do it, but let's try it, shall we? All right, so let's think about each of these. The function for female, that distribution for female, is a logistic regression. So female we'll treat as a Bernoulli variable, just like in your homework. So the logistic regression that's an empty model just has an intercept, and I have to start to build an EM algorithm. The first step is to just make wild guesses as to what the parameters need to be. So I have an intercept in that regression. I'm going to set its value to 0. I could set this to a random value. I don't care. It should work. If EM is built the right way, it should converge. So 0 here for female for the intercept. Now let's look at the model for CC10 given female. That's a simple linear regression where CC10 is predicted by an intercept in female. I have values for both of those regression coefficients. Similarly, the prediction of performance given CC10 in female. Now, these are all main effects. There's no interactions. I have a 0 for the intercept, 1 for CC10, and 1 for female. With me so far? Finally, um, the last model has usefulness predicted by performance, CC10 in female, plus there's an intercept. So those full values are listed there too. Okay, now this is where things get real fun. We need to figure out which values are missing, because in each step, in the E step of the algorithm, we're going to take the expected value for each of these missing data points and change it with what the predicted value is from the regression. Okay? So each time we're sort of imputing data using a regression single imputation, but then we iterate to an M step and repeat the process. So it's even though one iteration of E to M is like a single imputation, because we're chaining them back to back, we achieve what's called the detailed balance, having both of this, having the algorithm converge to what it should be in practice. It's sort of one of the more novel understandings of missing data that came out of the later part of the 19th or 20th century. So here, each of these is missing. That tells us who we need to impute data for. So I'm going to set up an ELM algorithm. Um, I call my algorithm data data 3, or I basically give my algorithm data that, because what I need to do is I need to impute the missing values at every step of the E step. So that algorithm data will not overwrite our original data going into it. And this is what happens. Let me flip to my R code here. All right. This is going to take just a second for me to get run again. And now I'm in my, this right here is the EM algorithm in my while loop. Now, again, I'm not expecting any of you to do this. I'm showing you this to sort of complete the book. Okay? So, the E step, we take each of our regressions and we fill in the missing data with what our predicted value for each will be. So, here, if we want to think about what a piece of missing data should be, in the logistic regression, the probability of someone being a female is set to 0.05 when the intercept is 0. So what I'm going to do is, for everybody missing on female, I'm going to just round that 0.05 to a 1. That's our expected value sort of pushed onto the space of where it needs to be. Now, for CC10, our predicted value depends on female. So these are what our predicted values should be. Remember, we have really stupid regression coefficients right now, zeros and ones, right? But I'm going to fill in those data. Okay? Same thing with performance and same thing with usefulness. And now if I go and look at algorithm data right here, you'll see usefulness, performance, CC10, and female are all complete. We have complete data. So now we've done the E step. Let's do the M step. In the M step, we calculate our logistic regression for female first, and we can take a look at our intercept. Our intercept is actually 0.33. That's what it's estimated to be for this iteration. Now, one thing I need to do is calculate its log likelihood, because I want to show you the joint log likelihood that comes from the factored regression, right? Remember, our joint log likelihood arrives at the joint distribution, but the log of this means it's the sum of the log likelihoods for each. So now I just need to calculate the log likelihood for female, giving us the component of this F of female part on the log scale. Right? So I do that right here. And log like female gives me the likelihood value for female. So what you'll notice, some of these values are negative 0.874, and some of these values are negative 0.539, and that's if the data are male or female coming in, right? How are we doing so far? That was regression number 1. Now we do regression number 2, CC10. That's just a linear regression. We can update our parameters. The intercept is now negative 0.547. The slope for female is 0.844, but we have a residual variance we have to estimate as well. And then we can go in and calculate the log likelihood with our normal distribution, right? So far, so good. So this is going to get really repetitive. Same thing with performance model, update parameters, update log likelihood, and our usefulness model, update parameters, update log likelihood. Now we've run 4 regressions, calculated 4 bunches of log likelihoods. I put that into something called a log-like matrix, which it doesn't want to show me. So this is each person's log likelihood under each of our factored regression models. The sum of these log likelihoods gives us for each person their person joint log likelihood for each person, and the sum of that across all the people gives us our full joint log likelihood. So if I take the sum, the row sums of the log-like matrix, that gives us each person's contribution to the joint log likelihood. And the sum of that gives us our joint log likelihood. That's one cycle of EM. How do you feel about that? Weird, right? You're like telling me that I could just do regression and I'm going to get to a place that works? Hold on. Guess what happens next? I now have an updated value of the intercept. So I go back and I impute all the missing data based on my updated parameters. And then I come in and now I have a brand new data matrix. So I now go and estimate new parameters for each model. And I have a new log likelihood, right? And we keep this process going and going and going. And let me show you what happens if we let this run. Let's do this. There it goes. Good question. Question in the chat. Missing about assumption about missing data. So in theory, this should give us missing at random assumption protection because we're actually using every case. We're imputing the values for every variable for every case as we go forward. So this approach handles the female distribution correctly. That's a terrible way of putting it. Handles the Bernoulli variable distribution very appropriately, but incorporates missing data protections overall. What you can see is this log likelihood as we go iteration by iteration gets closer and closer and closer to some joint value. I'll note that value is not going to look like Levon because Levon does not have a Bernoulli distribution in it, right? So we can't compare the two. In fact, if I allowed for more iterations, take a look at what happens to our algorithm here. Whoops. That number, oh, I didn't reset everything. That's the problem. Start this starting values. Take a look at what's happening to the EM algorithm, right? Far away, and then we start getting closer and closer and closer and closer. And then the final value of that, we can say, what's our female model? Right there is our proportion to females, we think. Logit version. We can have regression coefficients for CC10, for performance, and for usefulness. Now, embedded in all of this is the model you're after, and so you could build a multivariate normal, you could build other things, but this is hard, isn't it? How many of you are going to write your own EM algorithm? Now, I was like, when I was in school, yeah, but that's my thing. I like estimation. I don't think everybody likes estimation. I kind of wish you did, but that's okay. It's kind of like, kind of wish my son, did a little bit more math or quit playing a few more video games. But the reality is he's not going to, and that'd be a battle. So it's okay. You don't like estimation. If you don't like estimation, you're welcome here. Everybody's welcome here. Just teasing myself here. No, seriously. How many of you think you might do an EM algorithm? Nobody. Okay, sounds good. Then that's the right way of doing it. Turns out when you have missing data like this, now we have these 3 methods for missing data: maximum likelihood, Bayesian, and multiple imputation. When you have variables of mixed type, like female being Bernoulli, the rest being sort of plausibly multivariate normal, the SEM approach and maximum likelihood's the hardest. Bayesian, you can build this directly into a JAGS program and it'll work much better. Beyond that, multiple imputation, the methods I'm going to show you, do allow you to impute variables multiple times using the right distribution, in this case, Bernoulli distribution for female. So it is possible to have better version of this with Bayesian and with multiple imputation, but using maximum likelihood under the SEM approach with variables that are mixed of the type of distribution is hard unless you're willing to write your own algorithm. Okay? By the way, probably could do this in Optum as well too, but we'll stop there for right now. All right, should we keep going? Great. Any questions on EM? Again, I'm showing you this to try to complete the book. Yes, question. If you have complete data, yeah, question. If you have complete data, in theory, you could go and use the SEM functions. In fact, you could probably use them just fine. The problem is female and Levon don't get along. So with complete data, you could use your own version of Optum to do a factored regression. It'd be a little more complicated, but you could do that. Basically, allow female to be its own distribution and then have the joint distribution of the three other variables be predicted by female. You could build it. I wouldn't. It's overly annoying to do that. But complete data, yes, you can do it. You would not use EM though. Good question. Any other questions? Okay. The next example from the book is interactions. Now, a variable interaction is really we're predicting an outcome with the product of two other variables, right? So it's almost like forming this third variable. So if I wanted the interaction of female and CC10, I would just make the product between two of them and multiply them together. So think of it this way. Interactions showed up in the book, and then there was a section about curvilinear effects or quadratic effects. A quadratic effect is similar to an interaction in that the quadratic is the variable times itself, right? Like an interaction of a variable with itself can be thought of in a quadratic sense. But the bigger picture is this: an interaction, anytime, if you think about what's happening in Levon in the SEM approach, if we did nothing, it's going to treat female as continuous and normally distributed. It's going to treat CC10 as continuous and normally distributed. Whenever you have a product of two normally distributed variables, though, the result of that is not normally distributed. So the problem with interactions is similar to the problem with incorporating female into the analysis in that we have a mismatch between the likelihoods assumption of what the variable should be distributed as and what the variable will be distributed as. And similar to that, the remedy for it is identical. But let me step through the process. He talks about using the just another variable approach. And this is one where I say the anti-Nike slogan, just don't do it. Don't do it. Right? Instead of just do it, just don't do it. Right? I don't know that that came across in the text. Clear, obvious violation of distributional assumptions. Now, if you're publishing in a place where nobody knows anything about distributions, you can probably get away with it. But if you're concerned about the accuracy of your science, not the publication, don't do it. Okay? But let's play it out. So I create an interaction variable, femxcc10, right here. And what you'll see in this interaction variable is that the interaction itself is missing if either CC10 or female or both are missing. So if you look at what I do here, CC10, female by CC10, and this observation that's missing here, CC10 was missing, but female was not. And then later on, you may have a female that's missing, but CC10 is not. Both of those are missing on CC10, fem by CC10, right? But we've created another variable, which gives the name, just another variable. Just don't do it. Just don't do it. Okay, but I'm going to show you. Going against not doing it. Uh, so now, as you might imagine, if it's just another variable, we need that other variable to go into the likelihood function as well too, right? So let's start with the regression. Our regression line has the interaction term in it now. And because femxcc10 is in our data, that's no problem. Levon will run that. But with it being just another variable, we want to put it in the exogenous variables as well. So we need to give it a mean. We need to have a variance, and then have a covariance with it and the other exogenous variables here, CC10 and female. So it is literally in the, why the name of this approach is called just another variable, because it's as if fem x CC10 were nothing to do with fem female or CC10. It's just another variable. Now let's estimate it. Now our warning again is the same warning we had with female, but all observations are being used. And you can see we're using 350 observations. It didn't say smaller amounts. This is good in some ways. The model is still saturated, so we don't have to worry about model fit. And now you can see the impact of it. And it turns out in this analysis, fem by CC10 does not have a significant interaction on either usefulness or performance. Again, we can take a look at all the model matrices. The main one being the fitted model matrix. You see no zero there. You can tell it's pretty much saturated, but we certainly can tell with the raw residuals and the normalized residuals being zero. All right, and we can visualize this model too. When we visualize this model, again, it looks like another variable, right? fx1, that's our interaction between the two, and that's how it builds throughout. Okay. Can you imagine how to do this with an EM algorithm? Slightly different, right? Oh, dude. Come on, Jonathan. Let's get to my code here. So really what we're doing with factored regression is the same thing. The only difference here is in factored regression, remember in the E step, we imputed female, and then conditional on female, we imputed a CC10. So what's happening in the factored regression is sort of similar to what will happen in the Bayesian algorithm, in that we're not imputing the interaction directly. We're going to impute each of the variables that are part of the interaction separately, and then make their product show up to make the prediction. So that's the one catch that goes differently here. And I'm going to spend a few minutes on it because it's preparing you to see how we do things both in Bayes and in missing multiple imputation, particularly with chained equations, right? So if you have an interaction in one of your models, and one of those variables is going to be missing, you impute the univariate variables and then form the interaction. That's sort of how the process goes. All right, let's take a look at what happens here. Again, the female model is just a logistic regression. The CC10 given female is a simple linear regression. But after we get to the E step of filling in female and filling in CC10, then we can do the full performance as a function of the interaction as well, because it's complete now. And the same thing with usefulness. Does that make sense? So here, the only change in my algorithm was when I get to, I have a few extra parameters, the interaction term on performance, the interaction term on usefulness. So therefore, I have to include those in our missing data imputation part. And then in the M step, you'll see that there's a CC10 by female interaction as well. And that value is needed to make sure it shows up in each of the models. As you can imagine, in this process, what's going to end up happening is the fact that we have another parameter here will change the other values, right? So our log likelihood result is not the same as we had before, right? It does change things. But you can see, again, the process goes about. We see a nice sort of asymptotic relationship. And now we can see the parameter estimates of our model, here being the the female by CC10 interaction of 0.04 and the female CC10 interaction 0.15 here. Now, again, this is not comparable to Levon because Levon doesn't have the same likelihood. So these numbers are not going to look exactly like Levon's. The other thing that I have here is in my factored regression here, I'm not estimating the joint distribution of performance and usefulness conditional on the others, right? I've sort of chained the equations to a bunch of linear regressions because it was easier to build with code for this lecture. So it also won't be different. I'd have to reconfigure some parameters to be able to make this the same. Are you following me? First question. So how many of you feel like missing data sounds fairly easy when it begin with, but as you get into it, it's not easy at all? It's the leading question. But how many feel that way? I'm gonna put two hands up. I feel that way. And you're chasing this ideal. Like, remember at the beginning of class, we said missing not at random, good luck. Missing it completely at random, that's a fairy tale. Somewhere in between is missing at random. So in trying to pursue the best missing at random process is really what I'm trying to teach you with this. And it's not easy, particularly from just Levon and SEM. You have to have better tools to get to where it's a little bit easier. Cool. So we continue. Any questions? Okay. Let's get into auxiliary variables. Remember in that big data file, we actually have four other variables we haven't used at this point. High school credits in math, math self-confidence, what is that? Math anxiety, and math self-efficacy. And it turned out, again, convenient because I'm controlling it for this for sake of example. I actually have complete data on those four variables. Like we gave a demographic questionnaire and everybody filled out every one of them. Now that never happens, but hear me out here, right? So now we can go and use those variables where we have complete data and build analyses with those so that now we have all of our, number one, all of our parameters, all of our missing data, all of our cases included in the analysis. But number two, have the best protection about missing because now missing this might be related to one of these variables as well too. So this is the sort of the best case scenario under maximum likelihood. Now with Levon, we're still going to have an issue with female. If female comes in the likelihood function, we're still going to have a problem because it's not normal, not normally distributed. But we'll just ignore that for now. Okay? So when we put the variables in, the goal with auxiliary variables. Now, at the end of the chapter, there again, here's one way of doing it. Here's another way of doing it. Here's another way of doing it. But start with the beginning of the parts of the chapter with auxiliary variables. And the key is this. Auxiliary variables should be saturated. If you just looked at the auxiliary variables by themselves, they're exogenous variables. So that group within auxiliary should be saturated. Every mean, every variance, every covariance is estimated within just the auxiliary variables. And then they also need to be correlated or have covariances with our outcome variables and with our predicting variables. Right? So basically, the auxiliary variables, if you think of a covariance matrix, our analysis before had four variables in, so it was like a 4x4 covariance matrix. And now we're adding another four variables, so it'd be like an 8x8. Right? So again, I'm going to put my hands up the screen here. The four, actually, I might even be able to use my pen here. All right. This was the original analysis right here with four variables in, right? And this right here would be our auxiliary variables. We want all of this to be saturated, but we also need all of this to be saturated and all of this to be saturated right here. So auxiliary variables have to correlate not only with each other, but also with all endogenous and exogenous other variables as well too. So when you add auxiliary variables, you add a lot of different parameters to the model, but the key being we need it saturated because it helps with model fit. And then we get the best situation there is when it comes to missing data. Cool? I don't know if it's cool. It's a lot of work, but yeah, science is a lot of work. So let's add those in. The auxiliary variables now are exogenous. We have their means and we have their variances. And now the covariances of auxiliary variables with the other exogenous, male and CC, or female and CC10, and I shortcutted those covariances, right? This is all the covariances of the exogenous variables and the auxiliary variables. And in this case, auxiliary variables are also exogenous, okay? So what this section is doing, the covariances, is like taking a look at all of this part of my matrix right here. And that's saturated. That should be saturated, okay? And actually, no, because female and CC10 were there, it actually is also incorporating this part up here. This is female and CC10. That's saturated, and all of this is saturated as well, too, in the covariance matrix. Then the rest of the model is mostly the same, right? We have our regressions that haven't changed, our residual variances haven't changed, and our residual covariance hasn't changed. But now we need the covariance between our endogenous variables and our exogenous covariances, right? Our new exogenous variable. So this is what shows up. And I want to make one other point here. You'll see those are the four auxiliary variables, but the full matrix I've drawn for you right here has 8, or in this case, each of performance and usefulness should have 7 covariances there. Well, there's 4 of them here. A fifth is the residual covariance, and the other 2 are the places taken by the regression coefficients. Right? That saturates our model. So this should be a saturated model. And when I say should, let me tell you this. When I was putting together this lecture, by the way, I was putting this together in Mannheim, Germany. It's great. Had a chance to work at the University of Universität of Mannheim Universität. It's nice. Everybody here was probably asleep as I was building this, and sure enough, I ran it and it wasn't saturated. So, and can you imagine how long I've been running these models? And I'm still going like, yeah, it's not saturated. I got to figure out where that is. I'm going overboard on saturated versus not because it's really easy. And you got to understand what model you're running to understand what the output is. So we're going to estimate our model. And again, saturated. 0 test statistics, 0 degrees of freedom. Hooray. Also, using all of the data. Hooray. So the only thing wrong with this analysis is that female is being treated as a continuous variable. The only thing. That's much better. So this is missing at random protection, but not supremely ideal yet because female is still continuous when it should be discrete. Okay. So now you'll note the log likelihood's much bigger, and that's because we have so many more variables in the likelihood function. The likelihood scale has changed. And again, we have a bunch of model parameters. I don't even describe those yet. You will note that these will be different than when we've estimated them before, though. And that's because we've put the auxiliary variables in the analysis. There are all of the parameters. We can check for saturated by looking at our residuals. Clearly saturated. We'll put R squared. And you'll see the R squared for performance has actually been going down as we go further. So we're doing worse at predicting. And I bet you're saying is, wait, things get worse? Yes, things can get worse if you handle it better. Usually when you don't do a good job with missing data, things look a lot better than they probably already are. But think of all the missing data examples I tried to give you. Polling data, weather data, all of it. Usually when it's missing, it's not a good sign, right? Not a good sign for conclusions. And we have our path diagram. So let me end here. I can't believe I made it through the handout, but I did. So here's the thought. My analysis decision strategy for you. I tried to build this into a path diagram and I couldn't get the code to work. So forget the flow chart. It's just a simple, straight, itemized list. Do you have missing data? If no, hey, do your analysis as usual. If yes, you got to get to the next step, which is you want to build your minimum goal should be an analysis that meets all the assumptions of missing at random. And so for maximum likelihood estimation, that means using likelihoods to your benefit. And so when you get to the next step, you have to ask, are all the variables with missing data, both in your model and auxiliary variable, plausibly continuous? Plausibly continuous. What do I mean by that? Can you think of them as being put into a linear regression as an outcome? Right? That's the test. Female in our example wasn't. So if you do have plausibly continuous variables, then using the SEM framework with Levon works fine. If you don't, some other SEM packages may work, maybe, but you have to dig into their manuals to figure out if they do. But finally, if you don't have that, that's where factored regression using Bayesian methods or the multiple imputation methods approaches comes in. So that's the big picture. When I read the chapter, that didn't come through, and I'm sitting there for weeks trying to analyze how am I going to teach this, and it finally came in. This is what I decided to teach with. It may not clearly it's not perfect. Nothing I do is perfect, far from it. But my way of sifting through the end of the chapter is this: the SEM framework's very helpful. It will handle most of or a lot of your analyses. Again, I'm going to look at your results to see what an example model might be for each of you to try to understand a little bit better about how your analyses might fit into this. Um, but in many cases, SEM is still going to be incomplete. That's where multiple imputation or Bayesian shows up. Okay, cool. How many of you can use SEM only with all of your methods? Any method that you might use? Probably not, right? Probably not. So homework 3 will be about this type of approach. I'll have another simulated data set. You'll be doing analyses, putting variables in likelihoods, checking likelihoods, and so forth. That's the content of it. It'll be under the SEM approach. There will be no EM algorithm. So, um, and then next week, again, we'll be talking about Bayesian, an introduction to Bayesian with JAGs. So I have a lecture prepared. Um, we use JAGs. Please read chapter 4. There'll be an assessment, a reading assessment I put out later today for that as well. Okay. Any questions for me before we end class today? Yes. Yes. The question was, what's the advantage for saturating the model? The advantage is model fit. Model fit becomes perfect in a saturated model. Now, the model that we are most interested in, for instance, we are most interested in this case, predicting performance and usefulness. That's our model. That's what we really want to get to. And it just so happened that was saturated, but it may not be, right? In practice, this might be a latent variable model. This might be some other model. And you may not end up being saturated overall. And that's okay. It's just when you add auxiliary or exogenous variables, you need to ensure that this sort of lumpy part of the covariance matrix is saturated. Otherwise, model misfit may happen. And when model misfit happens, you may have bias in your parameter estimates. Does that answer the question for you? Excellent. So I'm not, all right. Other questions? This is the perfect time to take a drink. Who's excited to get to Bayesian? That's my question for you. Anybody? All right. That's what I'm looking for. Who's faking excitement? I'm just kidding. I'm excited. I love Bayesian statistics. And I'm weird. I know that. And so I tell you things that I don't expect you to always be able to do. But if you're interested, I hope that those are the sort of the breadcrumbs for where to start if you want to go down a little bit more interesting path. Okay. Thank you for class on Zoom. Thanks for being present. I'm hoping that next Wednesday we won't have winter weather problems to deal with and we can all be back in person. It's great to see you, though. If you have any questions between now and then, don't hesitate to reach out. I respect every one of your questions and I respect each of you. Thank you. Have a great rest of your week. Take care.